Hi everyone, good morning. So, if you are all there, you can just sign in very quickly. Okay, so I know you're all there. I just tried to give you 10 minutes so that, it's 9 o'clock. It's too early for you guys, I guess. So, it's too late for me, but it's too early for you guys. Okay, so today we are going to jump ship a little bit. We talked about metagenome, whole genome analysis, and we talked about how a minimalist approach, how can you just sequence only 16S RNA and then get a quick look at the composition of a sample, microbial sample, um, gut sample or soil sample or all the microbes in water and that kind of thing. So So, what we're going to do today is we're going to talk about clustering and classification algorithms in general, because if you think of anything we're trying to do in biology, we are clustering and we are classifying it. Either we are clustering things by population, we are clustering things by disease, we are clustering things by microbial subcommunities, we are classifying sequences, we are classifying proteins that are similar functions in sequence, in cluster W, that's what we're doing. So it's always about clustering, putting similar things in a bin and classifying things, similar things in a class, right? So it's always about clustering and classification. So for clustering and classification, it's not just in biology. You know now that the whole machine learning and artificial intelligence, everything is about learning and classifying, and not just genomics data. Medical data, people are trying to classify them so that they can predict whether a given drug will work for a patient or not. In Amazon, they're classifying and clustering so they can predict what I may be interested in and send me some advice as to this has come into the market. Would you be interested? They're clustering and classifying my buying pattern and my spending pattern and that kind of things to target their audience. Marketing data, inventory data, everything eventually needs clustering and classification. So there are many tools that's already developed in in other areas of science by computer scientists or by mathematicians. These algorithms exist. In genomics, we need to adapt that. So let's first understand some of the simple algorithms you may already been taught by Srivatsan. If you haven't been taught, he will come and teach you in the third semester, I'm thinking. In statistics, some of the clustering tools have already been taught in statistics as part of statistics. I will just introduce them a little bit so that the biggest thing in genomics is how do we change the sequence data into numbers. Once you have numbers, you can do classification and clustering using any tool that's already existing. Okay, so let me switch to my PowerPoint mode right now. So we are going to be talking about clustering and classification in genomics. You may have already done few things. Let me change to the next slide. Oops, sorry. Okay. So pretty much clustering and classification in a very, very simplistic way, right? Why is it a problem in computers, right? Because when you look at the 1D, there are two examples I'm giving here. Okay, hold on. I'm losing my mouse for some reason. Okay. So there are two examples I'm giving here. 1D, there are points on x-axis. It's going from here to here, and there are points from here to here. By just looking at it, you can tell that there are two clusters, right? Our eyes are really capable of seeing the clusters very clearly, okay? But for computers, if you give the x coordinate of all these points, it can tell whether there are two clusters or three clusters or four clusters, right? It has to find a method to cluster them. Then it will say that, okay, I got three clusters, two clusters here. Again, in the two dimension, I have this many dots here, okay. By looking at it, you can say, yeah, approximately there are three clusters. But if I give you a Excel spreadsheet of x and y coordinates of all these points and don't plot it on a 2D plot, you won't be able to tell whether there are three clusters or what. When you're giving the coordinates of the point to the computer, it doesn't see it. It just has x and y, x and y, x and y of each point. So somehow it has to find out that there are three clusters or four clusters. So computers always have to compute distance between points to know how to cluster them. So there are many methods to do that. So, one of the, let me go to the next slide. Go to the next slide now. Okay. So when you're computing distances between points, um, of course, there are methods like, actually this slide, let me see what's next. Okay, I'm going to go to this slide. So there are many clustering tools. Okay, hierarchical clustering, principal component analysis. You may have heard about it, and K-mean. You may have heard about it. Can somebody type in while I'm still continuing to talk to let me know whether K-mean and principal component has been done in the statistics class or not. Okay, based on that, I will go into the detail. Okay. So in any event, hierarchical clustering, I know you guys have done it. This is with respect to producing multiple sequence alignment in second semester. Okay, so it hasn't been taught. Okay, so I will introduce some, and I'm pretty sure it will get covered in your statistics class somewhere down the line. But I will cover it in a very conceptual way so that you can understand better when actually it is taught. Okay, so hierarchical clustering. The video is not working properly. He's saying. Hmm, okay, what should I do? Um, hmm. Hold on one second. Let me call Afia and talk to her. Hold on one second. Hey, Afia.
Yes, ma'am. So currently the internet is a little slow here, so everybody's video streaming is buffering. So they're not able to follow.
Only today. Yeah.
Yeah, only today, only now, like from few minutes. So give us some time. We'll try to fix it.
Okay. Khan, you call,
Yes,
call Khan?
yes, yes, ma'am.
Okay, okay. So let me know until then it fixes, okay? Yeah?
Okay, okay, ma'am.
Yeah.
This gets
Okay, bye. they're having technical difficulties. They're having technical difficulties. Okay, so yeah, I'm checking whether it's working for you guys. Afia, is it
Yes, ma'am.
working? Is it working?
Yes, ma'am. I
Okay,
can see you talking to me.
okay, okay. Bye, bye.
Yes, ma'am.
Okay, so I'm hoping you guys are seeing what I'm seeing. So I was going to tell you about clustering, all the clustering tools that we usually use in metagenomics and genomics. Hierarchical clustering, you already know that from the second semester when you did multiple sequence alignment. Um, you had to convert the multiple sequence alignment, the sequences, into some kind of numbers, because between two sequences you have to compute a distance between them, right? So the way you did that was something called edit distance. So wherever how many mutations are there, you counted that number, and that will give you the distance between two sequences, aligned sequences. So somewhere you have to convert them into some numbers. In BLAST and other sequence alignment tool, you have this mutation matrix that converts them into number, and some models that converts them into numbers. So eventually you have to convert everything into numbers before we do clustering, because then the machine can take it and cluster it by using Euclidean distance. Majority of the time we use distance computation to do the clustering. So in principal component analysis, what happens, since you guys said that it's not covered, okay, let's go to that slide. I already talked about how machines may be finding it difficult because machines don't have eyes, so they have to compute distances, and they have to use an algorithm to tell you how many clusters are there. What you can see very clearly, a machine cannot say it clearly. So that was the point I was trying to make. So in principal component analysis, what happens? Yeah, I'm going to go to this next. In principal component analysis, what happens? In the example where I gave you the points, there's a 1D point and a 2D point. In practice, what happens is you have vector of many dimension. Like each vector can have 5 or 6 components, not just 3. In a Euclidean space, what happens? You only have, for each point, you have x, y, and z. Correct? Okay. So you have 3 dimension. That's called 3 dimension. In 2 dimension, you only have 2 components, x and y. But in general, in a complex data set, you have multiple dimensions, maybe more than 3 dimensions. So sometimes a vector can have 10 dimensions. So it will be 10 dimensional space. But when you're computing distance, you don't have problem with that because what's the formula for the computing distance? It is, if I have 2 points, I'm going to write it down. Let me pick my pen here quickly. Okay, I'm going to write it right here. Okay, for example, you have x1, y1 is a point here, x1, y2 is a point, and x3, y3 is a point. Okay, distance between x1, y1 and x2, y2 is computed as x2 minus x1 whole square plus y2 minus y1 whole square root of the whole thing. Okay, that's the distance between point 1 and point 2. This is point 3. Okay, so D12 will be this. So now we have only 2 dimension, right? X and Y. If you have X, Y, and Z, if we have third dimension, then the same formula will become Z2 minus Z1 whole square. That is in the third dimension, distance between point 1 and point 2. Okay, so you can keep on theoretically, although it is hard to imagine how a fourth dimension, a fifth dimension, sixth dimension will look like, but mathematically you can keep on extending it. From 1 dimension, you went to 2 dimension, you went to 3 dimension. So if I have a vector of 10 components, like let's call it um, A1, A2, A3, A4, A5, and so on. 5 components. And the second point is this is vector 1, first vector. Then the second vector is B1, B2, and so on. So the distance between the second point and first point will be B1 minus A1 whole square plus B2 minus A2 whole square plus B3 minus A3 whole square, B4 minus A4 whole square, B5 minus A5 whole square keeps on going. So the distance computation for an n-dimensional vector, okay, so here it's 5 dimension. So you could really have an and then you have bn. So this is the n-dimensional vector. So in mathematical representation, it doesn't matter how many dimensions you have. You can compute a distance as long as you know, know the component of every one of them in every one of those dimensions. Component of a point in every one of those dimensions. Okay. Which slide? Which slide up here? So are you getting it? Are you getting the multi-dimension thing? Right? Okay. So in multi-dimension there is another problem. Okay. Because it is not in 3 dimension. Okay. So here the again what I'm trying to say, because Affair wants me to repeat this. I'm thinking maybe you guys missed something. So all I'm trying to say is when you have, hold on 1 second. Hello Saptarati.
not clear the last part you told, the multidimensional thing. There was problem with the mic or something.
Okay.
So
okay, I'll repeat that. Okay, I'll repeat that. Thanks. Bye.
I think you have to repeat from the start only.
Okay, bye. Okay. So, okay. So I'm getting it now. Okay. Let me see what happened in the previous slide. Where was I? Yeah. So you guys got the 1D and 2D thing, right? It's a two-dimensional point. You only have x in the 1D. You have only one component: x1, x2, x3, x4, x5, x6. That's it. It's on the x-axis. You see that, right? You see that on the x-axis. The points are not there in the y-axis at all. So it's this one in 1D. This is the 1D thing. Okay. In the 2D thing, you have points, it has x component. So this point has x component here and a y component there. This point has x component here and a y component there. So this is in 2 dimension. Okay. So what I'm trying to say is, when you go into an abstract data set, okay, you may have multiple dimensions. If in the third dimension, for example, suppose this is 1D and 2D, right? Third dimension, you will have x, y, and z. Everybody can visualize 3 dimensions, right? Every object has x-axis, y-axis, and a z-axis. You have 3 dimensions. So, what I'm trying to tell you is, when you're computing distances, every clustering tool has 2 components. One is, you divide the data set into vectors. That's the first step. Once you have the vector, you compute the distances to do clustering. Every clustering tool will compute distances between 2 data points. In this slide, I'm going to repeat. In this slide, we have, let me erase the mess so that I can start making a mess again. Okay, so you have point x1, y1. This is in 2 dimension again, right? x1, y1, x2, y2, and x3, y3. So this x1, y1, distance between x1, y1 and x2, y2, I know you guys keep forgetting how to compute distances. That's why I'm writing it here. Okay. The distance between, this need to be erased now because this is not there. This is still in 2 dimension because I'm repeating what I had said before. So I'm going to go back and scratch it again. Okay. So distance D12 between these 2 points is x2 minus x1 plus y2 minus y1 whole square. Square root of that is the distance between point 1 and point 2. This is in 2 dimension. That's why you have only two sets here. Suppose we have these points were in 3 dimension, where this one has a x1, y1 and a z1, and this one has a x2, y2 and a z2, and this one has x2, y2 and z3. Then D12 will be equal to x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So the reason why I'm showing this is, in 2 dimension you have only two of them. 3 dimension there is 3. So now mathematically, although more than 3 dimension, it is hard to physically imagine how those points will look like. In mathematics and in clustering algorithm, it doesn't matter. You can have vectors of many dimensions. For example, you can have the first point, the coordinates of the first point, so the component of the first point in all the dimensions are A1, A2, A3, A4, A5, AN. Okay. And the component of the second point is B1, B2, B3, and Bn. Component of the third point is, let's say, C1, C2, C3, and so on. Cn. This is an n-dimensional vector. It's not 2 dimension, it's not 3 dimension. It's n-dimensional vector. Okay. So what will be the distance? What will the distance of this will be? It will be distance AB, let's say, will be A2 minus A1 whole square plus B2 minus B1 whole square, and it keeps on going to Bn minus An whole square. Square root of whole, that is the distance. So now as long as each point has large number of vector, you can compute the distance between them. And this is pretty much what we're going to use in clustering. Any method you use, this is what we're going to use in clustering. Okay. So going to the next. Are you getting it? I think you may be getting it by now. Okay. So in principal component analysis, what happens is you have the vectors that are in n dimension. I'll tell you some examples of the vectors, how you get n dimensional matrix in biology or any other space. Okay, you got n dimensional vector and you're computing distances. Not all distances are independent. Okay, not all distances are independent. I'm going to go back to the previous slide to show what that means. Okay, meaning that um, if you have a point, you have a space x1, y1, z1. If you have a point on space, you have a coordinate for that. There will be defined coordinates for that, and everybody will understand where that point is. But if I'm giving you a distance set, that's why I had this previous slide. When I go to the previous slide, when I erase all this, and I'm going to make a point here. Okay. What happens is, let me pick a pen again. Okay. So in this slide again, when somebody gives me x1, y1, x2, y2, and x3, y3, I can take a graph paper and I can plot a triangle. And the triangle will look exactly the same way no matter who plots it. Okay. But if suppose I'm not given x1, y1, x2, y2, and x3, y3, okay, I'm only given distances d12, d13, and d23 and d13. Okay, d12 is good, d23 is independent, but d13 cannot take any number. For example, suppose I'm saying this distance d12 equal to 3 inches, okay, and d23 equal to 5 inches, okay. D13 cannot be 14 inches. Cannot be 14 inches. You're getting it? Because even if you draw it down 2 inches here, okay, 3 inches, D12, and then you're drawing 5 inches here, you're drawing 5 inches here, you're drawing 5 inches here. D13 cannot be, this is 5 inches, this is 5 inches. So you're trying this is D13. Okay. At the maximum D13 can be only 8 inches. Are you getting it? Yeah? At the maximum D13 can be only 8 inches or less, depending on whether there is an angle between the two distances. If they are straight, it has to be 8 inches. So, D13 is not independent. D13 depends on D12 and D23. So, in the distance space, there is a dependency. For example, let's say there are 10 points. Okay, there are 10 points. Okay, there are 10 points, and 10 points have coordinates x, y, and z. So there are 30 numbers. 30 numbers, right? X, Y, and Z together, there will be 30 numbers. These 30 numbers for these 10 points defines the points perfectly where they are in the space. Okay. But if I give you the distances between these 10 points, how many total number of distances will be between 10 points? Do you know that formula? N times n minus 1 divided by 2. That's the total number of distances between 10 points. That is 90 divided by 2, which is 45 distances. So, between any given 10 points, you have 45 distances, but only there are 30 numbers. So, if you have a Cartesian coordinate, okay, if you have a Cartesian coordinate, let me go open a free. I don't know why my mouse isn't going anywhere. Okay, I got now an empty slide where I can draw. So I want you guys to do this exercise. When you have 10 points, when you have 10 points, okay, 10 points in Cartesian coordinates, Cartesian coordinates, you have 30 numbers, right? Okay, and I know Tyagarajan sir and Yatindra sir would have talked to you about internal coordinates. Internal coordinates, that's also 30 numbers. Bond length, bond angle, and dihedral angle. Okay, that defines the complete space. Then there is a third in distance. That's also called distance geometry. Okay, in distance geometry or distance space, you have 45 numbers. Obviously, these 45 numbers are not independent. And that's the point I was trying to make in the other slide. Between D12, D23, only D12 and D23 are independent. D13 is dependent on the other two distances. That's called triangular inequality. Okay? Triangular inequality. This is the big thing in distance geometry. Triangular inequality. So, some distances depend on other distances, and that dependency makes the distances not embeddable, meaning that if you have large number of points and you're computing all these distances, because the distances are dependent on each other because of this triangular inequality, what will happen is those distances cannot be represented in 3 dimensions. When you're talking about principal component analysis, the principal part of the component is very, very important. What it's telling you is a multi-dimensional space has component in many, many directions. Means it is an n-dimensional space, so it has component in n dimensions. But when you're plotting a principal component, because you want to visualize your cluster, and our brain and our visual capabilities are limited to 3 dimensions. We cannot appreciate n dimension. Although mathematically we can compute distance and everything, But when you want to see the clusters, you want to see it in 3 dimension. Because of this triangular inequality, we can embed n-dimensional points into 3 dimension by using the three principal components, meaning that where the points are most separated in the first dimension, second dimension, and third dimension, and you're forgetting about the fourth dimension and fifth dimension. You're saying, I don't care about it because this is too much, I cannot even visualize it. So, however, you can have many, many clusters, but for visualization purposes, we only are going to look at the 3 or 4 components that we can embed that. That's where the principal component analysis comes in. Because all the data in any space you take, not just in biology, every one of them are going to be multi-dimensional vector, and the distances are going to be such that they are not going to be embeddable in 3 dimension. Okay, so we are going to only use 3 principal components from that. So I will tell you how it is done. Okay, I think that's all I will be able to do today because we already got delayed here. So let me switch to my PowerPoint mode again. Yeah, you're getting it right. How did you calculate Cartesian internal to 30 numbers? Okay, you have 10 points, right? Okay, you have 10 points. The question from Mansa is how did we compute 30 from your 10 points? Each point in Cartesian space is a 3D space. Okay, 3 dimensional space. In 3 dimension, one point will have 3, right? X, Y, and Z coordinate. Correct? So each point will have 3 X, Y, and Z, 3 components. So you will have 30 numbers representing 10 points. Right? X, Y, Z for each point. So 3 times 10 is 30. That's how I got it. Okay. So now, okay. In principal component, let me get rid of all this. Yeah. In principal component analysis, what happens is I'll tell you how do you get a multi-dimensional vector also is part of this lecture. But as long as you're able to see that, okay, for example, from 3 dimension to 2 dimension if you have to go. Okay. If you have 3 points, but in the projection, if you're viewing down, suppose you have x-axis and y-axis, and you're looking from the top, although the points are raised up, but when you're looking from the top, you see only 2 dimension, right? You see only x and y. So the projection is what I'm talking about. So you have an n-dimensional vector, and you have to project it into 3 dimension. How do you do that? Which are the 3 dimensions that are most conspicuously separating the points, separating the cluster? That's what the principal component analysis basically does. Okay, so distances have to be embeddable into 3 dimension. So the way you do that is to compute eigenvalue. Eigenvalues are a methodology where you can compute a metric matrix. Metric matrix is the distance matrix only. Okay, metric matrix. The element of the metric matrix MMIJ. Metric matrix is a distance matrix of n-dimensional space. I already told you how would you compute the distance between 2 points in an n-dimensional space. It will be b1 minus a1 whole square plus b2 minus a2 whole square plus b2 3, and it keeps on going. And that will be the distance between point A and point B. Point B and point C again will be c1 minus b1 whole square plus c2 minus b2 whole square all the way. The only point what we have not done now is how do you come up with those components? How do you say that point 1 has this many dimensions? What are the how is data converted into that point? But for now, you just imagine in an abstract way that each vector has n dimension. When you do that, then you have a distance matrix. The metric matrix of distances is defined as each element Mij. Matrix is a square matrix, right? Distance matrix is square matrix, correct? Distance matrix is going to be a square matrix because you have point 1, 2, 3, 4, 5, 6. Here you have 1, 2, 3, 4, 5, 6. The diagonal will always be 0 in a distance matrix because distance between the point to itself is always 0. There is no distance between them. Then you have a D12, D13, D14, D15 distance. Here D12, D13, D14, D23, D24 and so on and so forth. So these elements, this is the metric matrix, this is distance matrix, but metric matrix is same thing as distance matrix where the components are given as half into doi square plus doj square plus minus dij whole square. What is the doi? Doi is you have a big space, right? Too many points sitting there. That's your data set. You have a centroid of a data set. O. O is the centroid of data set. Imagine a centroid of a data set and each point, the distance of each point from the centroid, which is doi whole square. Okay. And distance of each other, like for example D23, this point D23, okay, distance of 2 from centroid square, distance of 3.3 from the centroid whole square minus distance of 2, 3 whole square. That will go in this element and this element, 1, 3 element or 2, 3 element. Okay, so I is 2, 3. For example, let's say here 4, 5 element. In 4, 5 element, what will happen is distance from the centroid to 0 0.4 whole square plus distance of centroid to 0 0.5 whole square minus distance between 0 0.4 and 0 0.5 whole square. Okay, half of that. That is the metric matrix. You have to compute the eigenvalue of the metric matrix. Eigenvalues, what it gives you is the component of all the points. As if in 3 dimension, if you plot all the points, you get the components. You can say, oh, on x-axis it's this much, on the y-axis this much, on the z-axis it's this much, right? But in multi-dimensional component, you have to imagine. Okay, this eigenvalues gives you the exact component of every point on the multidimensional space. When you sort the eigenvalue by the biggest eigenvalue will be the axis on which all the points are maximum component. The second eigenvalue, less component. Third eigenvalue, even less. Fourth, fifth and sixth, there are less and less component of your space, data space on those components. So you only take the first 3 components and then you, every time if you look at a paper, all the published paper, you will look at the principal components only in 3 dimensions. What it means is the 4th, 5th and 6th dimension, they just ignored it. And they're only computing 3 components and they're giving you a picture, nice picture, saying that, oh, this population, these things are clustered here, these things are clustered there. Because that is something visually you can understand. Getting it? This is something I can repeat when I come there. If you guys don't get it, I can repeat. This is kind of tough one. Okay. So I do understand that conceptually it may be difficult because you have to abstract it out. N-dimensional space coming back to 3 dimension. Okay. So principal component analysis, you will use it many times in data analysis and NGS. In fact, for RNA sequencing data, let me check this time. I don't have much time. But for RNA sequencing data and everything, you always come up with principal component to show that, look, all these vectors for the cancer sample, they are clustered together. All these vectors for normal samples are clustered together. Okay, what are you taking in RNA sequencing? What are the what are the components? What is the n-dimensional space? Your n-dimensional space in RNA sequencing is the number of genes in the sample. Like in human genome you have 25,000 genes, correct? Okay, the expression of every gene is one of the components. So your vector in gene expression analysis, your vector is of dimension 25,000. Talked to you about one dimension, two dimension, three dimension. Three dimension you have x, y, and z. Imagine a vector of 25,000 long. Okay, in gene expression analysis, in sample 1, if it is a cancer sample, I have a vector of 25,000. In second cancer sample, I have a vector of 25,000 because I know the expression data for every gene. And third cancer sample, I have a vector of 25,000. And then I have 3 or 4 normal sample. Again, in normal sample, I know the expression of every gene. So I have a vector of 25,000 again. So now I'm computing the distance between two samples. Can you imagine that? Like you're computing the distance between two samples. That means you're computing each x, y, and z or every gene's expression. There are 25,000 numbers. So your distance computation will be 25,000 subtraction of 25,000 number, cancer to cancer or normal to cancer or something. And then you're saying, then you are embedding it in 3 dimension. Okay, and nicely showing the principal component saying all the cancers are clustered here and all the normals are cancelled. When you do it practically in class, I think you will understand it better. I'm going to leave the class today. You guys also go read our packages of beautiful principal component analysis. There may be some written theories behind them as well. Read that, and maybe I will repeat this a little bit, slightly differently in the next class, and then I'll go through the other procedure. This is the concept you need to understand before any other clustering makes sense to you. Got it? Okay. Okay, so I'm going to stop now because I think it's already, yeah, already only 5 minutes for the next class. I don't want to take it any further. So just clearly think about when you're walking around, when you're eating or something, what is the 3 dimension and n-dimension and how the distances come into play. Think about it because everyone has to understand it in their own way. Okay? Okay. Bye now. It's getting late for me here, so I'm glad we got something done today with the technical difficulties and all that. So I'm hoping I can see you guys on August 13th for the class. I'm not sure whether I should do the class directly or I should still do it via the streaming. But because in streaming I have a recorded thing available too. So thank you guys. Bye now.